Hey everybody, I'm here with tonight's homework video. In this video there will be 3 questions I will ask you. You can either write them down and bring them into class with the answers, or you can text them to me via Remind. Once again, there will be 3 questions posed to you. Today's topic is differential equations. Those are obviously equations that involve differentials. Anyone remember what a differential is? Well, if we have a statement like dy dx, that's a rate of change that means a little bit of y over a little bit of x. Each of those individually, if I were to split them apart, dy is one differential and dx is another differential. It means a little bit. A little bit. So, with differential equations are equations that relate rates, like dr dt, and quantities, like r. And we'll talk about how they all get connected together. What we're going to do is we're going to use these relationships between rates and quantities, and we're going to do some integrating to make the rates go away. So that instead of having rates and quantities, our equations will just relate quantities. Yes, I think I spelled that wrong, but we're not going to worry about it. It's going to relate 2 different quantities together. Okay, so once again, differentials, a little bit of something, differentials are little bits of something, dm, and differential equations relate these differentials with quantities, r, t, and m. Okay, now there's all different levels to differential equation properties, and we're going to talk about the main kind, which are the pocket problems. I'll explain why they're called pocket problems later on. And there's a very straightforward method of solving this first type, and these ones we're going to talk about now are the most common type. So let's take a look at one of them. Okay, so here's the most classic and common type of differential equation problem. What I have over here is a petri dish filled with bacteria, and as time goes by, the more bacteria show up, and the population grows, and the more the bacteria there are, the faster the population grows. As a matter of fact, it's a sentence you're going to see in almost all of these problems. And it's going to say the following. It's going to say the rate of change of population is directly related to the population. Now, these type of problems are often known as exponential growth or decay problems, and you're going to see why. But the rate of change of population is directly related to the population. So I'm going to break this down into 3 parts. First of all, I know that there is a rate which is related to a quantity, and the big key here is directly related. Directly related means as one gets bigger, the other gets bigger. As one gets smaller, the other gets smaller. So in starting these differential equation problems, I'm always going to pick a letter to assign to my quantity. So I'm going to call my population P. Okay? So guess what I'm going to call my rate of change of population? It would be the rate of change of population, dP, over dt. That means the rate of change of population with respect to time. And because they're directly related, I know there's some relationship between the two of them. I'm going to write down dP over dt is equal to, it's related to p, but it's not exactly the same, and this is the key. There will always be a constant that relates the two. dP over dt equals kp. Now you're going to see a ton of problems set up like this, but they're always going to have the same words in them. Let me just show you another quick example. Okay, so oftentimes we'll have a tank. So let's say we have a water tank, and we have water pouring into the tank. And it says the rate of change of water in the tank is directly proportional to the actual water in the tank. You're going to see this phrase all the time. The big key here is directly proportional. And so I'm going to assign my water a letter. I'm going to call that P, W. And I'm going to call my rate of change of water in the tank dW dt. No more W primes, because we can use the longer version. And the key is that they're directly proportional. So that means that dW over dt is equal to K, some constant, times W. Now, not that it matters, but coming up as a side note, we'll soon be coming to problems where they say things like the water are indirectly proportional. If that's the case, and don't worry about that for this problem, it's not that dW dt is kW, that's directly proportional. Inversely proportional will look like this. We may even hear future terms. I know I'm getting ahead of myself. We may even hear things like it's directly proportional to the square of the water. It would look like that. Or maybe it's going to say is inversely proportional to the square of the water. So directly or indirectly determines where the K is, if it's on the, sorry, where the W is, if it's on the top or the bottom. And then other features along there, but we're not going to deal with those right now. We're going to go back to only for today our directly proportional problems. So let's go back to this one right here. Okay, back to our relationship. We're always going to start off with some sort of differential equation, which looks like this. Now, as the problems progress, they're always going to give us numbers to substitute in later on, but we're always going to start solving without the number. We are going to solve this differential equation. Okay, I'm going to flip pages for a minute. Now, there are 3 steps to solving differential equations, and I call this a SIS problem. SIS. It stands for separate, integrate, and then solve. Oh, I didn't need to write right there. And the reason we're integrating is we're going to have differentials, and integrating makes differentials go away. Solve. Now, just for right now, just follow this one along. We're going to go over this together later on. But we're going to remember the 3 steps: separate, integrate, and solve. So I'm going to write my differential equation I have right now, which is dp over dt equals kp. Okay, so the first thing I'm going to do is I want to get all, separate. I want to get all the p's and dp's on one side. And then I want to get all the t's and dt's on the other side. Now, to begin with, I have this dp, and I have k and p over here. It doesn't matter which side k is on. I usually leave it over, I usually put it with the p's. And on the other side, you can see here I have a dt, but I don't have any t's. If I did, I'd move them over as well. So how am I going to solve this one? So I'm going to separate the p, which is a quantity, which stands for population, and the dp, which is a rate, part of a rate. It's a differential, which stands for the rate, the change in population. And I'm going to, on the other side, put the t's, which stands for time, which is a quantity, and dt, which stands for change in time, which is a rate. The sides you put things on doesn't really matter. My suggestion is put your initial quantity, the big number on the one, not big number, the thing we're trying to solve on one side, and t, which is time, on the right side. It just tends to make these problems a little bit easier. So I'm going to start by moving things over that look like they make the most sense. I need the dt on the other side, so I'm going to multiply both sides by dt. Cancel, cancel, and now I've got dp equals kp times dt. Okay, what do I want to move next? I want to get the p to the other side. I don't want to create a fraction out of these things, so instead of just dividing by p, I'm going to multiply by 1 over p on both sides. And now I have 1 over p dp equals, so just as a quick side note before I keep going, any equation that starts out with the rate of population directly proportional to the population is always going to solve out this following way. Now, some questions on the AP, you don't have to write out all these steps. Some you do, but you're going to see they're going to be easily reproducible as we go. So what I've done now is I've done that. I've canceled on this side. I've got 1 over dp equals k dt. K dt. Okay, I've now separated p's, dp's on one side. K's I left there, and dt's on this side. I usually put everything extraneous with the time. You don't have to, but it just makes it easier. And now I've done my separating. So what I'm going to do next, I'm going to integrate both sides. I'm going to integrate both sides. Now, the key here is I'm integrating the left side based on p. And I'm integrating the right side based on t. Okay. So what's the integral of the 1 over something? Well, that happens to be the ln of the absolute value of that something plus c. There's no numbers in here, that's why we have to add that in. Equals, this is like having a constant here. What would be the integral of 3? Well, the integral of 3, just as a quick side, 3 dt would be 3t, because the derivative of 3t is 3. So guess what the integral of k is going to be? It's going to be kt plus c. Okay, I gotta be careful for a second. Kt's always going to show up, so always remember you're going to see kt. There's a constant on the left side and a constant on the right side. They're not the same constant. They may be different, so I'm going to call this one C1, and I'm going to call this one C2. I'm going to come back over to here. I've now separated, I've now integrated, and now I'm going to solve to get a relationship with P based on T. So I've got to solve this equation. I'm going to bring it to another page. Hang on, I'm going to rewrite it. Okay, so I brought it over here. Once again, don't worry about memorizing these steps right now. We're going to reproduce it as time goes by. Just see if you can follow each little thing that I do right now. So my goal is to get P by itself. So the first thing I'm going to do is I'm going to subtract C1 from each side. And now here's where some understanding of constants are going to come in. This is some constant, it's canceled, it's gone. This is some constant added or subtracted from another constant. No matter what I do with those constants, when I combine them, I'm going to get a new constant. I'm going to temporarily call that C3. I don't know if it's positive or negative, but I can put a plus sign there. The sign can change on the inside, whatever I want it to be. So now what I have is I have the ln of P, ln of the absolute value of P, is equal to kt plus C3, meaning it's some other constant. It's not necessarily the first one, it's not necessarily the second one, but it might be some other number. So I'm trying to get P by itself. I can see it's ln in there. Well, how am I going to get that to go away? I'm going to E both sides. And what's going to happen is these are going to cancel out. And I'm going to get the absolute value of P equals E to the kt plus C3 by E on both sides. So once again, this next step is not something you know to do off the bat, but I'm going to just take an aside with this piece right here. What do you know that E to the fourth times E to the fifth is equal to? What does that go to? That goes to E to the 4 plus 5, which is E to the ninth. So 2 multiplied are the same as one thing with the two things added together. This piece of information right here, and like I said, you wouldn't necessarily know to do this until you've seen the problems. This is equal to E to the kt times E to the C3. Now here's where we blow up the problem a little bit. C is a constant, C3 is a constant, E is a constant, some constant to another constant is just some other constant. So I'm going to call that C4. I'm going to call this the absolute value of P equals I'm going to call this C4 equals C4 E to the kt. Once again, the reason I could do that is that E to the kt E to the kt plus C3 is the same as E to the kt times E to the C3, because we're adding those things together. Okay, I'm going to bring it to another page. I've got the absolute value of P equals C4 EKT. Oh, took out that absolute value sign. So what if I asked you what the absolute value of 5 was? What numbers would give you what numbers would be equal to that? Could I put in for P? I could put in -5 or +5, and I'd still get the same positive answer out of there. As a matter of fact, that means that P, the actual value of P, is equal to plus or minus, because it doesn't matter what's on this side, it's going to be absolute positive, plus or minus C4 EKT. So this may seem a little strange. C4 is just some constant. Whether that constant was positive or whether that constant was negative wouldn't make a difference. So in essence, no matter what that is, it's just some other constant again. And as a matter of fact, I'm not going to give it a number this time. I'm going to say that the answer is P equals C E K T. This is the general solution for any directly proportional relationship. And I call it a pocket problem because if you look, you kind of see pocket. I know it's not perfect, but it's close. You notice it is an exponential equation now, and that makes sense because we know with population, We know with population, as the population increases, the rate increases. That's something that's exponential in nature. So that's why we get this equation. So this is what we call the general solution. For any rate directly proportional to the quantity problem, and I always call it the pocket problem because it almost looks like the word pocket is there. The first thing to be able to do is get a general solution, and we'll work on doing these steps. And then what happens is from the general solution, you'll get a specific solution. But that part's usually the easy part, and I'll show you what I mean. Well, actually, now that we know how to do this, it's actually pretty easy to go to the shortcut. Let me show you what the next step would look like. Okay, usually what they'll do is they'll give us two pieces of info. More often than not, they'll give us what's known as the initial condition. And then they'll give us a second condition. And we'll use those conditions to get what we call a specific solution, meaning it'll solve for C and it will solve for K. Now what you're going to see is going to happen is it's usually pretty straightforward as to what the C is going to be. We're always going to use our initial condition. If we have an initial condition at time equals 0, we sub that in first and watch what happens to the problem. So I know when t is 0, I know population is 4,000. Watch what will happen here. Equals C, E, K times 0. Well, what's K times 0? K times 0 is 0. What's E to the 0? Well, E to the 0 is 1. So 4,000 equals C. Hey, that was easy. I now have the first part of my problem. P equals 4,000. C, not C, E, K, T. And here's the big thing, the initial condition. The initial condition is almost always C. So if they give you an initial condition, you know what C is. Now I'm going to use the second part to get the K, to find the K. And the nice thing about this is you don't have to find it as a number. You can just do the math and see what you come up with. You don't have to simplify. So when the population is 10,000, let's bring this to a different page here. When the population is 10,000, the time is 10. So we've got 10,000 equals 4,000 e to the k times, I think it's 10? 10. All right, times 10. So I'm just going to rewrite that as 10,000 equals 4,000 e to the 10k. That way I write it the other way around there. So I'm going to try to solve for k. So the first thing I'm going to do is I'm going to divide by 4,000. 4,000. That's a comma. By the way, that cancels. If you want to cancel this, you can. If you don't want to, you don't have to. So I've got 10 over 4 equals e to the 10k. I want to make the e go away. What's the opposite of e? Well, I would ln both sides. And now I get ln of 10 over 4 equals 10k. So now can I get k by itself? Yep, I can solve for k by dividing by 10. And I get k equals ln 10 over 4, terrible, over 10. And that's pretty much all you have to do to get the solution. You can leave it in that form. I now have my specific solution, which is, now it gives me the equation, instead of having the initial equation, which was dp over dt equals kt, which related a rate to a, a rate to a quantity. I now have a new equation, p equals 4,000 e to the ln of 10 over 4 over 10. Did I do that right? Yep. 10 t, which now relates the quantity population to the quantity time. Okay, so here are your three questions. Number 1, and this is an audio question, I'm just going to say it. Text me or write down any example of a differential. Remember, differential is not a rate. It's just one part of the rate. It's only one of those little pieces. Just write down an example of one of the ones from this problem. So you're going to write down one differential. Number 2 is, what are the 3 steps to solving a differential equation? Sometimes they're called diffie-Qs. That's the shortcut for them. solving the Diffie cube. Give your hand there on the page way back. I'll zip there really quick so you can see it. Almost. Ooh, we did a lot today. There it is. There's the 3. And the last thing, question number 3. You pretty much know what your C is going to be by looking at the blank condition. Pretty much know what the C is by looking at the blank condition. You can look back in the problem and see. It's a long video, a lot of work, I know. This way we've got the initial lesson done. Don't worry if you don't understand all the steps yet. We'll work on that together. And I shall see you next class. Goodbye.